Hello, hello. Hi, hi. Hello. Okay, good evening, friends of Rust. Welcome to our today's meetup, Rust. First of all, thanks Stefan for making this possible. Also, thanks a lot Mike for all the effort regarding the filming. And today I have the pleasure to introduce to you Ralf Jung, who's a professor here at ETH at the Department of Informatics. And he's also part of the language. Please help me a bit.
I'm in the language team advisors and co-lead of the Rust operational semantics team.
Thanks. Good. Thanks a lot for coming here, Ralf, and the stage is yours.
Yes, thanks a lot for the nice introduction, and thanks you all for coming, and however many more people are logged in virtually. I'm happy to talk a bit here about a topic that's near and dear to my heart, both kind of in my free time and in my research. I think a lot about unsafe Rust and the abyss that hides there, and the ways we can, well, the things we can do to make unsafe Rust kind of safer. This is meant to be interactive. I'm hoping for tons of questions because otherwise I will not have enough material to fill 45 minutes. So please ask away anytime during the talk when I say something that's unclear. I hope at least some of the things that I say will surprise some people here and encourage some follow-up questions. Can I close the door? Thanks. All right. So let's start with the usual kind of high-level selling point that we tell other people about Rust, which is that Rust is a memory-safe language. So the compiler guarantees that all sorts of bad things do not happen in your program. The program is not going to access memory out of bounds or out of time. It's not going to execute the wrong code by executing some kind of shell code or whatever nonsense might happen. It's not going to have any data races. A bunch of pretty fundamental flaws that plague software all day and that cause security issues and crashes do not happen in Rust. That's the idea. Except, of course, there's a big asterisk here, because there is this thing called unsafe code. And in unsafe code, you can do all sorts of nastiness, like take a pointer to something, do some arithmetic to take it out of bounds, and then do an access. And now we do have an out-of-bounds access, even though this is Rust. So most of the Rust code out there is completely written in safe code. This talk is not concerned with that. This talk is concerned with the, I don't have data, 1%? I don't know, the small fraction of Rust code that has to use unsafe for various reasons. Unsafe exists for good reasons. We need it to be able to write low-level, high-performance code that's correct for reasons which are too complicated for the compiler to understand, but it's a very sharp knife, and we have to be super careful in how we use it. So let's start a bit by seeing just how sharp this knife is. Once you start writing unsafe Rust, guaranteeing memory safety, guaranteeing all these nice properties is your responsibility. And this like a nice way to think about this is that you're kind of entering a contract with the compiler where both parties have obligations and kind of rights or privileges. And the key obligation of both sides is that on the one hand, the compiler is obligated to generate a binary that when you run it, does the thing that matches the source code you wrote. But there's also an obligation on your side, which is that you have to follow the rules. You must not do things like that. You must not perform out-of-bounds memory accesses or all sorts of other things. And this obligation is not to be taken lightly. If you break that obligation, all sorts of weird stuff can happen. This might look like a nice magical wonderland and a good drug trip or something, but really it's more like a nightmare drug trip in all reality. I just didn't want to induce fear in the audience by taking the appropriate picture. So let's get Firefox to open things in the right window, maybe. Let's look at one example of the weird things that can happen. So here's a little function which obviously will always return true. Right? We are testing if some integer is either less than 120, equal to 120, or greater to 120. There's no way this function cannot return true. At the bottom of this here is a little thing, a little main function which calls that function. And then if it returns false, states that the bad thing happened. And if you run this on current stable Rust, now I hope the demo gods are with me, then the impossible has in fact happened. This is the kind of stuff that happens, that can happen, when you break your part of the obligation. Do not ignore the obligation. Of course, the annoying thing is that in many cases, like if you change this code just a bit, maybe like that, then the impossible will not happen anymore. So it's not like you can rely on strange stuff happening. It's just sometimes strange stuff might happen. And it might not happen on Mondays, but it might happen on Tuesdays. So this strange stuff happening, you failing to uphold your obligation as an unsafe code author, that is what we call undefined behavior in Rust. And you might have heard a related term, which I want to briefly talk about, even though most of this talk will be about undefined behavior. The related term is soundness. So soundness is a property of a function that you write. Like imagine you are a library crate author, you're using some unsafe code internally, but you're a good citizen and you want to expose safe to use functions to the outside world. Something like this call me function, which of course is completely silly to use unsafe for that. This is just for purpose of demonstration. So what does this function do? It takes a shared reference to a Boolean. It does some pointer casting to turn this into a raw pointer to type U8. So we can kind of look at the underlying bits and bytes of the Boolean. We do a load, we check if it's 2, which it shouldn't ever be because it's a Boolean. And if it is 2, we call this hint unreachable unchecked, which is kind of the ultimate form of undefined behavior. If that code ever executes, we have immediate undefined behavior. And so reaching this line is an immediate violation of your obligation as part of this compiler-programmer contract. And this function is sound, because no matter which kind of safe code you will write, a shared reference to a bool will always be true or false. It will always be 1 or 0. It will never be 2. So even though there is unsafe here, this unsafe is kind of safely hidden behind a typed API that uses the Rust types to express the constraints needed to make this thing safe to call. Right? If you replaced bool by U8, this function would no longer be sound. Of course, if we change this a bit to maybe a raw pointer version of this code, like a star const here, then this might change. So what do you think? Is this still sound, or do we now have an unsound library? Unsound. Yes? Yes? Maybe I should, people raise hands. Who thinks this is still sound? 1/2 of a vote. Who thinks it's unsound? A lot more votes. The majority is right. Yes, this is very unsound. Like one of the ways we could break it is by creating a reference to 2 and turning that reference into a raw pointer and passing it to call me. All of those things, creating a reference and then turning it into a raw pointer, are possible from safe code. So this is sufficient to demonstrate that this library is answered, because we've demonstrated a safe client where the bad line has been reached. In fact, the bool here is kind of a red herring. Even if I remove this thing here, that's still unsound, because I can just take an arbitrary random integer, cast it to a raw pointer in safe code, and pass it to this function. So this thing is unsound for all sorts of reasons. To summarize the key terminology here, undefined behavior is a property of an entire program, a thing with a main function, something you can run. And the property is, well, undefined behavior means it violates the rules. Whereas soundness is a property of a library. So those properties talk about talk about objects of different type. A library is sound in approximation, there's an asterisk here, if you cannot use it to cause undefined behavior from safe code. I will not go into the asterisk now. If we have a bit of time left at the end, I'm happy to talk about that. But this distinction is crucial. It doesn't make sense to ask if a function like call me here has UB or not, because this is not code you can run. It takes inputs. You need to first supply some inputs. So this is important. Now I want to go over briefly a list of kind of common things people get wrong about undefined behavior. And this is by far the most common one. People test their code, they run their test suite, they write their whole program, they put it on the internet or something, and they say, my code is fine, I tested it, so there can't be any undefined behavior. And we've already seen the example earlier, right, where I changed the comparison a bit so that always return true, still return true. That program still was wrong. It was just now, it happened to be the case that the arbitrary thing the compiler did, and is allowed to do when you violate your contract, was actually the thing you meant it to do. That can happen, and that's almost the worst thing that can happen, because then you think you are safe. But you're not. Anytime you upgrade your compiler, you change your flags, you change anything about the dependencies, this can be arbitrarily unstable, and behavior might change again. Another common thing you hear in these discussions is people starting to talk about what the hardware does. What the hardware does is utterly irrelevant when we talk about undefined behavior. The kind of the rules for what you can and cannot do in Rust are stated on the level of the Rust language. They don't care about hardware concepts. And the link between what the final program produced by the compiler does and what your source program does, while it might look direct, is actually very, very fragile. The compiler is doing tons of amazing things to make your code go fast, and you probably want that, otherwise you would write assembly. And you would have to do register allocation by hand and all sorts of other fun things. But because that link is so fragile, the very concept of looking what your program does on the hardware only makes sense after we have established that we don't have undefined behavior. You can never argue with hardware things before we first made sure that there even is any kind of connection between your source program and the output. And such a connection only exists if you satisfied your part of the obligation in the contract with the compiler. So what the hardware does is irrelevant. Some people also say things like, well, I upgraded my compiler, my code broke, evil compiler. I mean, we try to avoid this, but when you have undefined behavior in the code, it's totally possible that it worked with one compiler and then stops working later. That's just in the nature of the beast. Some people think undefined behavior is something that compilers or compiler writers spend like days and weeks to find in your program, only to backstab you and break your code. That's not how it works. Compiler optimizations are just written under the assumption that there is no undefined behavior. And well, when assumptions get violated, weird nonsense happens. So it's not like compiler authors willingly withhold information from you, knowing your program has UB and not tell you. That's the opposite of what happens. They don't know if your program has UB or not. They just assume it doesn't. And then if it does anyway, weird shit happens. You might think this all sounds terrible. Why should we keep up with this? I should just go back to C. C is all the same game. There's no difference in undefined behavior between C and Rust. It's all the same problems. And if you use inline assembly to maybe you think you can do out of bounds memory access in inline assembly, there are some things you actually can do, but you have to be super, super careful. It's not a free pass. There are all sorts of assumptions that the compiler, C and Rust alike, makes about how the entire program works. You cannot break those with inline assembly. So with inline assembly, you are almost always just making your life harder. And finally, I disable optimizations so UB can't be a thing that works. Even without optimizations, there's a whole bunch of stuff going on. Even basic things like register allocation can kind of break when you have undefined behavior. It's true that without optimizations, it's much less likely that undefined behavior affects your program behavior, but it's by far not guaranteed that it doesn't happen. And it's still very, very possible. Oh yeah, and I also saw that, I think, at some point. It's fine if I put unsafe around it. That's not what unsafe is for. Unsafe doesn't mean undefined behavior is allowed. Unsafe means it's your responsibility to not have undefined behavior. Outside of unsafe, it's the compiler's responsibility or the responsibility of whoever wrote the library that you are using. Inside unsafe, it's your responsibility. Undefined behavior is never okay. It's just not a thing. Does anybody want to add any more or have any questions about this? Yes?
There's a funny story about the third point where the Clang LLVM guys try to make sure that the this pointer in methods can never be null. And that broke a huge number of projects who relied on that, especially Node V8, for example.
Yes, yeah.
They had to roll it back again.
Right, UB can, so for the people on the stream, there was a change in Clang to kind of make the compiler exploit that this can never be null. Turns out many programs have this be null, including V8, which is kind of important, and so they rolled that back. Yes, that's one of the problems with widespread misunderstandings about what is and isn't UB. So I said it's all the same mess in C. I would argue the mess is a lot worse in C, because in Rust we are, or at least strive to be, and there's people working on that, very strict and precise about what is and isn't undefined behavior. And also most people don't have to think about it because most people write safe Rust. Whereas in C, it's a lot less clear. Like undefined behavior is everything not mentioned in the standard, which is already kind of a weird way to go about this. A lot of undefined behavior also is mentioned in the standard. Also, nobody reads the standard, and the people that do don't understand it, including myself. So I think we are in a better situation in Rust because we are closer to having a very precise understanding to what is and isn't UB. The nature of the problem, though, is the same. So I hope it's clear now that knowing these rules about what is and isn't UB is absolutely crucial when writing unsafe code. You shouldn't be writing unsafe code without understanding the part of the rules that applies to the kind of unsafe code you write. You don't always have to know all the unsafe rules when you write unsafe code. If you're just calling get unchecked, which says that you have to have your index in bounds, that's all you need to know. If you start using raw pointers, you need to load it. You need to know a lot more. If you're using transmute, just don't, I hope. But if you do anyway, and sometimes there's good reasons to, you need to know a lot more. Thankfully, there is a tool that can help you. This tool can't replace knowing the rules, but it can help you learn the rules, and it can help you gain confidence that you followed the rules. This is a tool called Miri that I didn't start it. It originally was started by a couple other people. I've been working on it for quite a few years now. It's called Miri, and it's basically a way to run your code and test it for undefined behavior. So it does the thing which earlier I said doesn't work. Like if you just build your code with the regular compiler and run it, and then it works, that doesn't tell you anything about undefined behavior. If you run it with Miri, that does tell you something. So specifically, Miri can tell if a given program or a test suite, which is just a program, kind of shows undefined behavior during this execution. Miri cannot, and this is important to remember, Miri cannot tell you whether a library is sound. Because to test if a library is sound, the least you have to test is that it doesn't cause UB for every possible input, and that's a few too many inputs for Miri to try. Miri is also very slow, so even if it's technically finite, it doesn't work very well. So you still have to have a good test suite to increase confidence in the Miri results, and even then you can still be surprised. But it helps a lot. So to ensure soundness, we need a theorem prover. This is something which is not decidable. It's not something you can just have a button and it will guaranteed tell you. There are, of course, tools that can help you approximate it and things like that. I mean, okay, so far there aren't such tools, but people are working on them. Undefined behavior, on the other hand, on a concrete program execution with a concrete sets of inputs and concrete choices for all the non-determinism is a decidable question which we can answer. But of course, if tomorrow the thread scheduler starts to work a bit differently, then maybe undefined behavior is like showing up where it was hidden before or something like that. So there's no guarantee that all the possible UB was found in alternative execution branches or other inputs of your program, but it helps a lot. One big caveat is that Miri is an interpreter for Rust programs. It executes kind of the Rust source code, or more precisely, one of the Rust IRs, mir, line by line. So if you call C code, Miri is like, I don't know what to do with this, and just stops. Miri knows a few well-known functions. If you're accessing an environment variable or opening a file, Miri can deal with that, but that list is not very long. If you try to talk to the network, it's already done. But if you're writing pure Rust data structures or things like that, you can get very far in testing with Miri. Miri is also, as I mentioned, very slow. So if you have tests which try like tens of thousands of inputs, you might want to reduce the number of inputs for Miri. But Miri has found tons of bugs in real-world code, in the standard library and in crates out there. We test the standard library test suite in Miri every day. A whole bunch of crates have Miri on their CI. It's really a thing you can use. It's very easy to install because it comes with rustup. Only on the nightly toolchain, so you can just add it as a component. And then if you're on the nightly toolchain, you say cargo Miri test or cargo Miri run, and then it does its magic. So to re-emphasize, one important point is Miri cannot ensure that the library is sound, so it's still worth knowing the rules. So the remaining time that I have, I would like to use to go over some of these rules, show a few example programs, and then run them in Miri and show how Miri catches the problem and hopefully answer any questions that come up about the undefined behavior in this program. But before we get there, does anyone want to, anyone have any questions about the general framework or things like that? Does not seem.
One question,
Yes?
like, is there a list of the rules? And then you know
Yes.
them, or is this like a research topic to actually
So,
make the question?
yeah, the question was whether there's a list of the rules or whether that's a research question. The answer is yes and yes. So both sides of the or are true. Well, I can open it now. I was going to go to the list of rules later. There is a page in the Rust reference, behavior considered undefined, which lists the basic rules. And then furthermore, I mean, one of the things it lists is if you call compiler intrinsics, for each intrinsics, there's documentation in the intrinsic. Like if you call unchecked add, it will say, well, this is UB if the addition overflows. And then every single unsafe function comes with a documentation that says what do you have to ensure when calling this function. And the implication here is if you fail to uphold this, it's undefined behavior.
So this is like a conclusive list, it's just very inconvenient.
Well, for these unsafe functions, that's a conclusive list. It's written in English, so it's not always completely clear what it means when the requirements are a bit less local. I mean, it's very easy for things like get unchecked, where it just has to be inbounds and then done. But some of these requirements are a bit less local than that. We will see examples. And also there's a big warning here at the top of the list, which basically is us hedging that we're not done yet writing the spec. This is ongoing research to make the spec complete. I should also mention that MIRI strives to catch all the possible bugs, but there are 1 or 2 deficiencies in MIRI where there are things you might do which it might not cause the undefined behavior. Those are very, very rare things to happen in code, but they happen. And MIRI tries to be conservative, as in MIRI will tell you undefined behavior for some things that we tend to allow later, but we don't want to kind of preempt community processes and community consensus on allowing that and kind of making people feel safe about their code just by having MIRI give it a check mark. That might explain some of the differences you might see between MIRI and documentation. Yes?
I have a question about this example of the 120.
Yes?
So I think in my opinion, one way this could work is that, and correct me if I'm wrong, that the compiler tries to optimize it, like say it's x less than 512, and then the maybe unlimit it generates a value greater than 512 because the invariants are destroyed, so to speak, and so that's why it can return false. Is that something that the compiler can do because we violate the assumption?
So what the compiler does in terms of optimization isn't really relevant. What's relevant is that you broke the rules and which are the rules that you broke.
Yeah, I know.
So the rules in this case is that there's some uninitialized memory here. If you run this in MIRI, we can say that already on this line, before you even start doing anything with the uninitialized memory, MIRI tells you, no, this is not okay. You're returning uninitialized memory here. It's returned at type U8. U8s have to be initialized, period. So from then onwards, the program is already doomed. If you want to understand a bit more precisely why we get this particular outcome, like which series of transformations in the compiler happens to turn this program from doomed by violating the contract into actually doing nonsense, what happens internally is that uninitialized memory is represented as a kind of unstable value, which every time you look at it can look different. It's a bit like a weird quantum kind of value. I mean, physicists in the room don't listen, it's not actually anything but quantum, I know that. So this is a thing that exists in LLVM and conceptually in many of these low-level IRs we use inside compilers. They have values which are different from every possible bit pattern that you could actually see in a real machine. And every time you look at them, they might look different, which represents the fact that LLVM, if it sees an uninitialized value, doesn't want to waste an entire register on that. So it might actually use different registers. Each time you look at it, it might use a different register, just picking one at random.
So that's what could happen.
That's what could happen. What actually happens here is then LLVM sees, we are asking if an unstable value is less than 120, and LLVM will be like, I guess that's false. And then we are asking it if it's equal, and it goes like, yeah, false. And for greater it also gets false, but for greater equal it says true.
Okay, so
But that's arbitrary choices. They could have done either way. They're just,
it's in LLVM.
yes,
But it could happen anyway in the stage.
yes. In the future, Rust will get more optimizations before LLVM happens. They might already do things here. Yeah. Did you have a question? Okay. Yes.
Quick follow-up question. If you can go down to the place where you call the function. So
Yes.
if I understand correctly, UB actually
Could you we'll head the questions into the mic because otherwise you have to talk like a parrot all the time. There was a question if Miri handles it as an option T or any other enum, but I think you answered that, right? It's just a magic enum unknown.
I mean, basically every byte in memory is an option U8 is the way to think about it. It's actually, bytes are actually a bit more complicated for pointer reasons I won't get into. But you can think of it as every byte in memory is an option U8, if that was the question.
Yeah, something like that.
So my question is, if I understand correctly, the UB actually happens on line 84 and not on the access to the variable, correct?
Yes.
Because I think in languages like C, C++, uninitialized stuff is quite fine as long as you don't actually access it.
That's very unclear. So in C++, they have a list of things you can do with indeterminate values, which is their name for this. And for example, passing them to a function is not allowed. So the UB would happen certainly the latest, the moment we're passing x to always return true. In C, it's not entirely clear enough. This will also depend on the type you are using. Like if you're using an int, then there's more optimizations allowed on int than on char. So maybe with char it's okay, but with int it isn't. The problem is that the C spec is a whole pile of English. And it's very easy to, in one place of the C spec, say something about, oh, indeterminate values also are a thing, and then forget to update every other place in the C spec where it now should say what happens when you see an indeterminate value, and it just doesn't say anything. What I can tell you is that Clang will add no undef attributes to every single function argument and return value. It might exempt char from that, I'm not entirely sure, but if you did this with int, then in both C and C++, if you compile it with Clang, there will be undefined behavior, and they think that's justified by the spec. Yes, Chris?
So, are you saying that undefined behavior?
We have a stream,
Just a
so.
second, yeah. So this is the first time we do a stream, and we don't have this nice throwball microphone yet.
Oh, okay.
And the mic is special.
So
Mouth close to the mic.
Yeah, very close.
okay. Give it a moment. I'll get used to it. So undefined behavior only happens in Rust if you have unsafe code. Is that correct?
That's a promise that the compiler and language teams make. Yes. If there's undefined behavior outside of unsafe, that's a bug in the compiler or in the library you're using.
So you're saying that everything that's unsafe, everything that's undefined is unsafe. As in, like, you cannot just have, there's no under-specification in the language. In a way.
I mean, there are other kinds of under-specification, as in non-determinism, for example. You can just, like, take the address of a local variable and print it to standard out. You don't need to use unsafe code for that.
Right, but that's not undefined behavior.
Correct.
Right.
So
okay.
there are weaker forms of under-specification that can happen in safe code, but there's very strong one.
Okay, because then that's really different to when we say that is undefined behavior in C, because in C, undefined behavior, like you said, is any underdefined behavior, basically.
Oh no, C also has undefined, unspecified, implementation defined. I don't even know the full list. It's
Sure,
just
but I'm
basically in C, all code is unsafe.
I'm saying when you say something is undefined, it doesn't automatically mean it's unsafe there.
But in C, everything is unsafe, so it does mean that.
You can't actually say that. Like you can say there's no safety guarantee given by the type system. Or
That's
by
what
the
unsafe means in
compiler.
Rust.
Sure,
Unsafe means
but
safety
you
is
can
not
prove
guaranteed.
it's safe, right? Like
Yes.
if you prove the absence of, you don't have to prove the absence of undefined behavior to prove memory safety, for example. That's what I'm saying.
You do. In C, you do, yes.
No.
Yes.
No, you can overspecify. Like not everything has to be defined in this in the C what's it called? Like in the C standard, you can have like deterministic semantics. Like everyone who's done verification on C has like overspecified things.
Oh, if you know your compiler, the compiler might, of course, say that certain things which are UB according to spec have guaranteed behavior.
Sure, but you
And
don't
then
even
you
have to
can
know
do
the
that.
compiler. You can just assume a more deterministic, we can take it offline, but basically what I'm saying is undefined behavior, according to your definition in Rust and in C, do not mean the same thing, it seems to me at least.
I think they mean the same thing. It's just like C behaves as if it was an unsafe block everywhere.
One is under specification, the other means memory unsafety.
No,
that's what you
that's
said.
not a difference.
Let's
That's
take
what I'm
that
saying.
offline.
It means memory unsafety in both of them. No, but Rust really, I mean, I don't like the term undefined behavior, but we took it from C because it's what people know.
Sure.
And if you're writing against an arbitrary unknown C compiler, like the only thing you know about your compiler is that it conforms to the spec, then all the same rules apply.
Yeah, we can take it offline.
Okay, let's look at some kinds of undefined behavior and how they look like in Miri. So, I mean, okay, I already briefly showed the uninit thing. The out-of-bounds access, that's the very first program I had in the beginning of the talk. And I mean, okay, this is hopefully not too surprising and not too hard. When you do the read, Miri will tell you, well, there's some allocation, it's size 4, you are at offset 4 and reading 4 more bytes. That just doesn't work. Use after free is also easy. I don't think I have to show the code for that. Out-of-bounds pointer arithmetic might be a bit more surprising. So if you read the documentation of functions like add, offset, or sub on pointers, then the documentation says that even just doing the arithmetic, if it goes out of bounds, is undefined behavior. This is just like pointer arithmetic works in C. And Miri will tell you that. If you're using add the wrong way, then you're doing out of bounds pointer arithmetic. There is another function you can use, which is called wrapping add, which doesn't have this clause. So with wrapping add, this program is now fine. However, just because you can do the arithmetic to go out of bounds doesn't mean you are actually allowed to use that pointer to access memory. Right now it even tells me the unsafe block is unnecessary. If I now do an actual read from this pointer, then that's still undefined behavior. It's just that the arithmetic wasn't the problem, it's now the access that's the problem. Yes?
So my question is, does it check the step size? So if you have a struct that's little more than an int, does it check if you add like 5 instead of 8 in the offset?
I mean, it precisely checks the bounds of your object. So yes.
in a list, in an array, does it notice when I go in the middle of some object instead of an exact offset?
That's allowed, so it's not going to complain about that.
Okay, thanks.
I mean, there might be other rules you're breaking inadvertently because data might look the wrong way or something, but in principle, in C, pointer arithmetic is limited to array things. In Rust, within an object, you can do pointer arithmetic any way you want. You just have to make sure once you actually do a load that you are in bounds and that the type that you're using for that load is the right one. I will have examples for that later. Insufficient alignment is one that people often get wrong. So here's an example. We are creating an array of 4 U8s, and we are casting the pointer into a U32 pointer. I'm using a bunch of methods here instead of the usual casts in Rust, because I think the as cast keyword in Rust is one of the worst things to use when using raw pointers. It will do way too many things and accidentally break your code. This way we have a bit more type safety. So what happens here is we have a 4-byte array, we turn it into a pointer to a single 4-byte integer. So in terms of bounds, everything is okay. This program still has undefined behavior because the array could be sitting at any address. The alignment requirement of such an array is 1, so the address has to be divisible by 1, which is rather trivial. Whereas integers have an alignment requirement of 4 on most platforms. So the address of every integer that you load or store or create a reference to has to be divisible by 4. And we are violating this here, and that's undefined behavior. Again, the same rule exists in C. It's just not that widely known. A common argument is that, oh, on x86, there is no alignment things on the hardware, and so I don't have to worry about it. Remember what I said earlier about what the hardware does. It doesn't matter. This is UB on all platforms on C, on C and Rust.
So this error right now says it's accessing memory of alignment 2. Is Miri guaranteed to detect this error? Or is this just by chance that this time it's not alignment 4?
Very good question. Miri is not guaranteed to find this error. because the actual address of this thing is random. In this case, it happens to be divisible by 2, but not 4. That's why this was the error. In general, it could only have been divisible by 1. So this is one of the cases where the non-determinism that occurs when creating a new object, creating at a random address, means errors might sometimes be found and sometimes not found. So one of the things that you can do is run Miri many times. It has a flag to change the random seed that's used for all the non-determinism. So you run it with a bunch of different flags, you get higher chances of finding bugs like this. Miri also has a special mode where it will treat alignment in a more symbolic way and is guaranteed to find bugs like this. Unfortunately, it might then also flag errors in code that is actually completely correct. I don't know a way to avoid that, because there's some code which does really wonky things, like imagine the code before, like it creates an array without any guarantees, and then it tests if the address is aligned, and if it is, then goes on. This would be fine, but in that other symbolic mode, Miri would complain. And there is code out there which does things like that. One of the things you can do if you're worried about alignment is that there is a read underlined function on raw pointers, which does not have the alignment requirement, which on some platforms will be slower, because on some platforms aligned reads are faster. But if you use read or the normal star, the alignment requirement always applies on all platforms. And it doesn't just apply when you do a read. Even just creating a reference already incurs a requirement, or even actually just writing star PTR, no matter what happens afterwards, incurs the requirement. So in this program here, Miri will still complain. Yes. Yes?
Which line is actually now unsafe? Is it line 2, line 6?
Line 7.
Line 7.
On line 6, we are creating a raw pointer, which is not aligned, and that's okay. Raw pointers, as long as you don't star them, are okay not to be aligned.
So
This is different than in C. In C, even just creating the pointer would already be undefined behavior.
okay, so read underlined is fine because it's okay.
Read unaligned is fine because it's based on raw pointers, and so there's no initial requirement that the pointer itself is already undefined, is already aligned. But even something like this, which some of you might have seen this macro, that's UB because we did star the pointer. This might change, this particular rule. I'm in favor of changing it, but for now we're keeping it UB so that we kind of have the option open of kind of reaching community consensus on some kind of coherent vision here.
So my question is, does the Rust compiler guarantee deterministic code generation for programs exhibiting undefined behavior?
No.
No?
We don't guarantee anything.
Okay. I mean, obviously the execution, like the program, like has can produce any kind of value, but like the code the assembly at the end, that is also non-deterministic.
I'm not sure if we guarantee deterministic code gen in any case, even for defined programs. We guarantee that the code gen that you get matches the program you wrote if there's no UB. Whether you get the same thing every time, I mean, certainly it changes with every update.
Yeah,
so
sure.
it changes with compiler flags, it changes due to inlining, due to all sorts of things.
Just, like for a given compiler version.
I think we want it to be deterministic, but you know, sometimes things happen where hashing is based on pointers, and pointers change because of address layout randomization, and then the iteration order in a hash table differs, and then suddenly the compiler gives you a slightly different output.
I can answer that. So, is that next to you? So the quick and dirty answer to that question is the standard Rust compiler, no, but there is a certified version that's engineered by Ferris, the Rust people in Berlin.
Ferrocene, you mean?
Yeah, Ferrocene, yeah, from Florian Ginke, and what's the other one? Ada, right? So they have a certified compiler that is generating the same output, but that's not available currently.
All right. Thanks.
Another point to consider here is that Rust has compile time code evaluation, and it supports unsafe code in its compile time code evaluation, so you can actually cause undefined behavior at compile time.
That's good point.
Just think about this for a second.
Yeah. Nice.
Okay, I'm going to do quickly over some of those. So invalid values are bad. Rust cares a lot about its types. Now we're getting into some kind of things which are UB in Rust, but not like that in C. I'm not actually sure about bool. It's a bit unclear. I think in bool for bool this might be UB in C as well, but in general C is less strict about its type. So turning 2 into a boolean is undefined behavior, even if you never look at that boolean. Just creating the bool is undefined behavior. This is important because there are optimizations which might introduce code looking at the Boolean even if you didn't write any such code. So we want to have that requirement always. Such optimizations occur very naturally. For example, imagine we had some kind of loop, and then in that loop we did an if x, and then the compiler realizes that this entire loop is, this entire thing, if x, doesn't actually depend on a loop variable, and wants to move the if x out of the loop. But the compiler doesn't actually know if the loop would ever run. Like the loop goes from 0 to I, maybe I is 0. So if only looking at if a bad bool would only be UB once you look at it, then moving an if out of a loop would not be a valid optimization anymore, because maybe the if was never executed, so the if was dead code, and we made it live code by moving it out. So that's why we have some of these rules where just creating bad data is UB even if you never look at it, so that we can do things like move loop invariant code out of a loop. And there are more invalid values. What do I have here? Characters, there's a requirement that char is a valid Unicode code point, so don't violate that. One of the lesser known ones is function pointers are non-null. So if you're interfacing with C code and you're representing a C function pointer, always use option of fn and Rust. Option of fn can be nulled, but just fn cannot be nulled. There is a guarantee that option fn will match the layout of a pointer in C. Miri can find data races. That's something I'm very happy about because I didn't implement any part of this. People just showed up, open source is amazing, and started implementing more and more ingredients for Miri to suddenly support all sorts of concurrency, which is not what I expected. But now Miri is very good at finding concurrency bugs and has found a couple of bugs in the wild, including data races and also weird behavior incurred by weak memory models, which is something you might have heard of and then you should be scared of it. But here it tells me that between lines 11 and 8, there is a data race because we're doing two write accesses which are insufficiently synchronized. And last not least, I'm not even going to show the examples here. There are rules about references. Shared references are immutable and mutable references are unique. Those rules are the most complicated undefined behavior rules we have. They are also very important and very unstable in the sense of we don't have a consensus yet for what they should look like. But they are important because they let us do very strong optimizations on references, even if we don't know where they come from, and we interact with other code we can't analyze. So they're super powerful, way beyond what any other programming language really can do. But they are also rather careful. And the short summary is, if you only use raw pointers, you are fine. If you only use references, you are fine. Don't mix references and raw pointers, then things become tricky.
I'm curious about the data race detector.
Yes.
You said Miri is an interpreter, so does that mean the detection is also undeterministic here? Or
it is, but not quite as much as you might think. So the detection is based on vector clocks, which means we don't have to have these operations actually execute adjacently. It works pretty much exactly like, what is the Valgrind-based detector called again? Hellgrind? No. There are two data race detectors for Valgrind. I forgot what they're called. They use basically the same thing, where you detect that an access happened and then later another access happened and there wasn't synchronization. There is still some amount of non-determinism inherent always when you have concurrency, where in some executions there might have happened to be synchronizations for other edges or I don't know, something like that. But it's actually much more deterministic than you might think, basically, in its ability to find these races. The more non-deterministic thing is that if you use atomics directly and you have this weak memory scary thing going on, then something that can happen according to the spec is that you read outdated values when you do a load. There's multiple possible things you could load at any moment. This rarely happens on real hardware, but it does happen. And Miri will just uniformly at random pick one of the values. And so there you might have to run your program a couple times to make sure they are all covered. Miri also emulates the weak compare and swap in the standard library, which is a compare and swap that might fail to tell you when it did successfully a thing.
That's the atomic visibility problem.
Yes, exactly. So I'm out of time. So for a more complete list, as I already mentioned earlier when the question came up, you can check the reference. Every unsafe library function must document their requirements. If you find a crate with an unsafe function that doesn't document it, the crate author did it wrong. And so with that, remember when writing unsafe Rust, always follow the rules. And if possible, use Miri to help you do that. Thanks all.
questions. I think we'll do 5 more minutes and then we'll take a quick break.
Mm-hmm.
And if you want to know where the toilets are, I don't know. Honestly, but
Yeah, so you mentioned that Miri stops when it encounters C code. My question is whether it stops completely or just for the C part and continues with like Rust. So I could imagine that like C returns you some pointers, so obviously it cannot reason about this pointer. But maybe later in code there are like pure Rust pointers that it can know something about. So
No, it just stops completely. I mean, like we can't know what the C function will do. We can't know which value it will return. We're just completely lost at this point. Maybe it doesn't have support for symbolic execution or reasoning about unknown values. So no, it just stops. There's not really much of an alternative here. There is some work in progress thing on doing some crazy libffi shenanigans to call the real C code without UB detection, obviously, to get its behavior and kind of what hasn't been implemented yet actually reflect this on the mirror memory, which should actually be possible, though it's kind of crazy. And then this will severely impact the ability to find UB also on the mirror side, but could go well with hand in hand with some of the existing things in Miri. So one thing I should mention is if you use pointer integer casts, or rather integer to pointer casts, A, don't. B, Miri will warn you, because once you start doing that, it won't be able to find all bugs anymore. The spec for those things is kind of not quite there yet. The spec we have is not something you can actually run. It's only something you can prove. And so Miri will warn you about that. And in C, it would just be a lot more of that kind of Miri possibly missing bugs around really weird pointer shenanigans. But Miri does support everything else in Rust. Like you can do, like, I don't know, crazy dyn table, whatever, something, unsafe pointer transmutes, everything should work.
Yeah, hi. One question. So in like microcontrollers and embedded systems.
Why is there always an embedded guy in the crowd?
I'm not the embedded guy, I'm just curious. So you have these things like, I don't know, input-output things where you just have to write to a specific address to make something happen. And then you have these libraries that like abstract that for you, but in the end they just pick a random address from a spec and write or read from it and have some like volatile markers around this. And you said hardware doesn't matter, but like how do these things go together? Is this all undefined behavior and it just works because we believe in it, or like
that would be bad, wouldn't it? I mean, so first of all, like Miri doesn't work in that case. Obviously, Miri has no clue that you have an MMO register at address 42. On the Rust side, no, this is not undefined behavior. The full way of making this formal is complicated, but basically we don't assume that Rust knows all the memory that exists. Rust controls some amount of memory. If you create a local variable somewhere, this is assumed to be completely Rust-controlled memory. But we are kind of working in an open world situation where there might be other memory that exists from the beginning of the program, kind of in the initial state, at addresses which Rust doesn't know about. And it is the responsibility of the surrounding runtime, or whoever else is part of setting that all up, that this memory never overlaps with any memory Rust understands and knows about. But assuming that is the case, it is completely okay to access that memory from Rust. You have to still follow the Rust rules, as in if you create a reference to that memory, all the aliasing things still apply and stuff like that. But it is okay to access memory like that. So in that case, yeah, there's a big asterisk according to what the hardware does. This refers to arguments of the form of x86 doesn't have alignment requirements, therefore it's okay to deref unaligned pointers in C when you compile only to x86. No. There were like, I think it was RAND, like some really, really big Rust crates which had a like if CFG bang to be like, oh, on x86 we just do the unaligned accesses, everywhere else we are careful. This is just not okay. It's always UB on all platforms. But if you have very specific environment kind of things, that's less about my CPU doesn't have data races or something. That's more about there's extra things in my environment that are outside of the control of Rust that I want to interact with. And then that's fine. That environment will probably set up extra rules. You might have to use volatile. There's all sorts of things that apply there, but it's in principle possible. Similar things happen when you start using inline assembly, for example.
We will do the last two questions. You had one and you had one, right? Yeah, and him.
Right. You said that MIRI doesn't have any support for sort of symbolic calculations. I was wondering, coming back to this FFI, if it would be possible to sort of specify the behavior of a foreign function, and then have MIRI like sort of bypass the foreign function based on those assumptions, even though it's not possible now. Like, is there anything in MIRI that stops that from?
I mean, of course, you could rewrite MIRI from scratch with support for symbolic values everywhere. That would be a lot of work because MIRI uses a lot of compiler infrastructure. The thing we do is that for well-known functions, like, I don't know, when you want to access an environment variable or print to standard out, MIRI is like, oh, I know this C function. It's called like getEnv. I will actually implement that. So we have we call them shims. We have a whole lot of these shims inside MIRI, which will then behave as if you did getEnv. So you do setEnv and you do getEnv, you actually see the value change. This is completely separate from the actual process environment, though we also have a flag which allows them to be synced. So like for specific functions, we can add support that way. Obviously, we can only do this for like big popular functions that have reasonable small functionality. If you link your C code with the Python interpreter and call that, we will not embed a Python interpreter in MIRI just to implement that shit.
Okay, did you have another question?
I was just curious what MIRI is. Is it an interpreter then, or okay?
Yes, it's MIR-E, the MIR interpreter, though we don't spell it like that. Right. It works on this IR level called MIR in the compiler. It's really basically just another front end for the compiler. Like it actually, well, backend, I don't know, code gen. It reuses all of the compiler infrastructure, but then instead of generating code, it just interprets it line by line.
Okay, so you can't like can't you just call a different interpreter for C at the points when C functions are called?
If you give me an interpreter for C that actually matches
exactly.
all of the undefined behavior and all of that.
No, I'm saying like, can you say given a function that would interpret the C, I just call it at the points when there are FFI calls?
You could, but this becomes hard once that memory is shared between C and Rust, because then the C interpreter might have to access the MIRI memory, and MIRI memory isn't just an area of bytes, because in the Rust spec, memory isn't just an area of bytes.
So you need the whole FFI compatibility.
Right, so you would have, these interpreters would have to be tightly integrated.
Right.
I think there is currently someone working, so there exists an interpreter for LLVMIR. It doesn't actually describe all LLVMIR UB the way MIRI does, but there is someone currently trying to wire that up with MIRI, as I found out when they reported that they get weird linking errors when they try doing that. So if you compile your C code with Clang to LLVMIR, something like that might work. But yeah, still very much work in progress.
So quick follow-up, is it plugin friendly?
No.
Oh, so no plugins.
No, we don't have a stable API. We don't have a stable anything. The Rust compiler isn't plugin friendly already. We really want to have the freedom to like rebuild and re-architect the internals. It's like the Linux kernel, right? There's no out-of-tree modules, which is not a thing.
I guess a bit open question, but let me give it a try. So there is a bunch of code that it's aimed to be compiled and to run as, for example, WebAssembly. But the way people test this code is they just write unit test to, like, you know, cargo test, and then it's compiled on their actual architecture they work on, like x86 or ARM or whatever. And then it keeps me in this place of discomfort that developers test the code all the time on different architecture they aim to deploy it. And I wonder if maybe here you have some advice that may be MIRI or maybe not MIRI related, what can go wrong, what to look after, what to do to protect against some things going nuts in such situations.
I mean, Rust is in general fairly portable. So like if you don't have UB, and if you don't have CFG target arch or target whatever in your code, then it should behave the same on x86 and WebAssembly. Some of the non-determinism might be different, like if you look at the addresses of the stack or interleavings of threads or something, those are different, but that's a problem even like between an x86 Linux and Windows, or even two Linuxes or whatever. But like most of Rust is actually very portable. But it depends a lot on the details. I should also mention one other thing MIRI is quite useful for. If you're doing low-level coding, one of the things that you might run into at some point is this funny thing called endianness, where some targets represent integers different from other targets. Because Miri is an interpreter, it can cross-interpret. So you can be on your Linux 64-bit little endian system, and you just say dash dash target mips something like the correct target triple, which might be a 32-bit big endian system, and Miri will run your code as if it were on that target. You can be on a Windows host and run it as if it were Linux. All these, like in principle, any possible combination there is possible there in terms of maybe just testing your code and making sure, like so like the bytes crate, I think, for example, uses Miri to ensure that it will also work on big endian targets.
Thank you.
Okay. So, would you like to announce the break?
In this
I
case,
can announce the break. There's a break.
It's now break. After the break, we will have Guillaume's talk. And when do we meet again?
20?
Yeah, let's meet. Let's meet in 8 minutes back here.
Have you unplugged my mic? Can I be noisy? Okay.
A software developer here in Zurich, and also here since 5 years, right?
Yeah.
Also doing Rust since 5 years.
Yeah, in my personal time.
The stage is yours. Thanks.
Thanks for the, yeah, I have my mic. Thanks for the introduction. So today I want to tell you about my journey using SIMD instructions in Rust with Android. And I want to start with a few questions to the audience. Who here has used Rust with Android before? Okay, 2 people. Who has used Rust with Android before? Okay, iOS, one person. And who knows what SIMD means? Okay, around half of the audience. So let's start with this question. What are SIMD instructions? And I'd like to start with going back to the lowest level of abstraction we have at the hardware, which is the CPU, which basically is combined of 2 things: registers, which represent memory, and operations, which are hardwired circuits into the hardware. 2 examples. Here on the left, you have a XOR, which you can imagine is going to have transistors bit by bit to compute the XOR over the whole register. On the right, you have an addition, which conceptually is similar to XOR, but additionally there is some carry bit to propagate throughout the register. So that's the basic block we have. And then with this abstraction of registers and operations, we have assembly code on top of which programming languages are built as a higher abstraction. So 8-bit is really a very basic CPU. Then over time, CPUs got more and more powerful, so 16 bits, 32 bits, 64 bits. And okay, at some point, nowadays, all modern consumer hardware is 64 bits, so you think, okay, well, did we stop at 64, or what is the issue? And the answer is no. We got wider registers already 20 years ago, but the fact is, okay, what can we do with wider registers of 128 bits? If you think about common operations you do with the registers, for example, pointers to address memory or a loop that you want to iterate through, 64-bit is more than enough for any kind of reasonable computation. So really, it didn't really make sense to use wider registers, which we could build in terms of more powerful CPUs, 128 bits, but divide it logically into an array of smaller lanes. So for example, here, 4 lanes of 32 bits. And at the operation level, we're going to take these registers and then, for example, do an addition of 2 arrays, element by element. So conceptually here, you have, again, some XOR happening and some carry bit that will only propagate up to the division of the block. And then there are even more exotic instructions that didn't really exist before, such as shuffling blocks. So for example, you take a wide register, here split it into 8 blocks of 16 bits. You additionally pass a shuffle parameter, and then you have an instruction that will shuffle the blocks and return a register with the blocks mixed together. Another example is a comparison, element by element, where you return zeros in this block if the elements are different, and ones if they are equal. So these are the building blocks that we got from SIMD, and then another question, what can we do with them in terms of algorithms? And why is it faster to use them? The primary example is a loop, and it's called loop vectorization. So you take 2 arrays or slices here in Rust, and you want to add elements of one into the other element-wise. So you can imagine that without SIMD, essentially you will have one addition instruction for each element in the loop. But with a SIMD instruction that can add 4 of them at once, you can divide by 4 the number of instructions, and so conceptually have the program run four times faster. So this gives you a speed up. Another example is, again, the shuffle I presented. If you want to do the shuffle manually, you can imagine that there will be many loads and stores and intermediate registers to use. Here, for example, 8 operations. And with SIMD, you just have all of that in one instruction. So again, you could have a program running 8 times faster with that. And it goes even beyond that. So mostly for cryptographic operations, there are some specialized instructions that will really compute a whole loop in one instruction. So here on the left, you have this example of polynomial multiplication, which, again, it's really a niche application for cryptography, but conceptually, if you want to handle the implementation, you need a lot of XORs and shifts and a whole loop. And here you have just one instruction doing that for you. So yeah, in short, with this building block of SIMD, you have optimized algorithms everywhere. For example, the hash map implementation of Rust is using, since a few years, this Swiss tables algorithm that was published 5 years ago, and that is combining all these building blocks to really speed up the hash implementation. I really encourage you to have a look at how that's implemented. That's really interesting. Other examples would be substring searching or parsing JSON. So all of these applications, go beyond the simple case of vectorizing a loop. You can really leverage these instructions in smarter ways. Any questions about that? All right. So now we want to use them and write algorithms in Rust that use this SIMD instruction. And the first challenge is to, call them from Rust, write a Rust program that uses them. So again, I take the example of an array of 4 elements that I want to add together. So this is the template of my code, and at the bottom I want to write this addition function of 4 times 32-bit integers. So I need to fill this. The first approach is to use inline assembly, which was recently stabilized in Rust. So you need unsafe code for it, but you don't need a nightly compiler. You can use the stable one. So let's try that. Well, the first challenge here, as you can imagine, is you have to find out what is the name of the instruction you want to call. So here, on Intel, for example, adding these two arrays, going through the vendor manual, you figure out that the instruction is this p-add-d instruction in assembly. So once you've found that, you can imagine, let's try to call it like this. And this is where you start kind of fighting the Rust compiler here in terms of syntax for the assembly. So here the first error you encounter is that you cannot directly plug in like arbitrary types into the assembly. It says only integers, floats, SIMD vector types or pointers are accepted. So you need to figure out what to do. Maybe since there are integers, let's try 128-bit ones. And here, I wrote this transmute, so I know that Ralph is going to cry, but it's just to illustrate, don't do this in the real world. Let's just imagine these are 128-bit integers. It still doesn't work because this register class, according to the Rust language, doesn't support wider integers. So then looking a bit more to the Intel's documentation, there is this XMM class of register, and indeed the Rust assembly macro has this class XMM-reg. So we're getting somewhere, but still it doesn't support my 128-bit integer. So the next thing is to go back to the nightly compiler and then use this portable SIMD type, I32 times 4, which was recommended by the previous error. And then when we transmute here, this time we get a different error. which is that the first argument needs to be mutable. Indeed, we had the second argument into the first one, so that's easy to fix. We had a mut. And now, okay, we get a weird syntax error. What does this mean? There's tokens and arguments. You know, it's hard to figure out what to do. And eventually, it was just a missing comma between the parameters. So you get the idea, like using this raw assembly, besides being unsafe, is also quite cumbersome to use. And yeah, I also didn't mention there is also these options you can add to the assembly, pure, no mem, no stack. I mean, you have to read the manual, make sure you uphold all the guarantees and things like that. So it's all very cumbersome. And that's where a new language abstraction comes into play, which is SIMD intrinsics. So the idea is to have functions that will wrap the low-level instructions together with the Rust types. They are defined in the core arch part of the standard library, and the naming is modeled after the respective vendor manuals for Intel or ARM or even other architectures. So let's say if you have a code from C++ that was using SIMD and you want to port it to Rust, you will use the same type of names, if you will. And so yeah, this should be really ergonomic because you just call a normal Rust function. So the way it works is something like this. So here on Intel, again, I have to convert to a vendor-specific type. In this case, is M128I with the underscores. So yeah, again, I'm lazy for the slides. I just transmute. Normally, you have specific functions to call for that. And the addition itself is this nice function. Well, the name is, a bit complicated. It comes from the Intel's intrinsics manual, but you get the idea. You have addition of 32-bit blocks, if you will. You still need an unsafe block for that, but it's much nicer to work with. Any questions on this? So okay, the second part and the second challenge is to write cross-platform algorithms from this. So here I take an example, another instruction. And the question is whether all these names are the same thing or not. Actually, even for each vendor, you have two different names. One is for the intrinsics, and one is a completely different one, is the instruction you would see in assembly. And the answer is yes, these are all the same instructions, but it's hard to know. So in practice, how does it work? Maybe you can try to compare the names. Okay, well, a few bits are matching, but it doesn't say much. Maybe you can check the Rust documentation. So, I mean, there are dozens or even hundreds of intrinsics listed for each architecture. So you have to read all of them. And then, well, even like these two that are similar, that conceptually should do the same thing, in fact, take vendor-specific types, and even the documentation itself is quite different. It's kind of taken from the vendor's manual. So yeah, there are a few keywords that are the same, but it's not so clear. So maybe let's take a look at the vendor manuals. Again, you have like a bunch of pseudocode, and in some cases you need to click through several links, and it's all like, I mean, English text mixed with pseudocode. If you read carefully, you might get an idea that this is what you wanted to do, but it's not obvious. So this is why, if you're going to write code with SIMD, it's really important to test and also benchmark it on real hardware to make sure you did the correct thing you intended to write. Benchmarking is also important because, let's say, not all SIMD instructions have the same costs. Some will take more cycles than others, so it's important to test that. Okay, so now I wanted to test, and well, on Intel I already have my development laptop, but I wanted to test on ARM, which is the other major platform. And yeah, essentially, either I would buy the most recent Apple laptop, which nowadays is based on ARM, or I just had this old dusty Android phone, my previous model. I mean, the screen is broken, everything is broken, except it still works. So it's much cheaper and eco-friendly to do that. So yeah, my plan was the following. I wanted to test some SIMD code for ARM. I will compile this code to the Android platform, then make sure that this device actually even supports the SIMD instructions, and then run tests and benchmark.
Could you step 2 steps to the left, please?
Yeah.
Another? Yes.
Hopla.
Thank you.
Yeah, so the next challenge was to use Rust and compile it for Android on user space. So you mentioned a few of you have tried that before, and yeah, it's actually kind of complicated in a way, but the workflow is conceptually the following. If you want to write an Android app and put native code in it, you're going to have a Java source code, which is kind of the main entry point, the main part of your Android app. And then it will invoke native functions into a native language, so in my case, Rust. The Java is compiled to Java bytecode, and the Rust will be compiled into shared libraries for all the CPU architectures that Android supports, which is these 4 ones. And then the whole thing at the bottom is what is packaged into the app. And then at runtime, the specific device you run on will load the native code for the architecture you have. And yeah, how to compile for Android, how to compile Rust for Android in 4 easy steps. There is a lot of steps, so I mean, the most obvious one, you need to install with Rust up the Linux Android targets. Then you need to install the Android specific native development kit. And it turns out that depending on the version of your Rust compiler, only certain versions of the NDK will be compatible. So recently the version was bumped, so you know that's the kind of thing you need to pay attention to. Then you need to configure it somewhere in the Rust as a linker and leave it in your path environment variable. Later you need in your cargo config to configure shared library output. And with all of that, you can compile code. But then the next problem is that there is no standard output. That is to say, you cannot call println out of the box from an Android app because yeah, just the Android system will discard std out. So instead, you need to use this JNI crate to call back into Java, and for example, this Android-specific logging class to write, you know, your test thing. So if you just want to do, you know, printf testing, you need to go through all of these steps. And yeah, this is just a quick hello world of how does this look like. From the Rust point of view, you need to define this special unsafe extern function, exported as a Java native function, and then call the functions you want. Here I wanted to illustrate, okay, did I even compile for the correct architecture? And Rust gives me with this target arch configuration flag the name of the architecture. So finally I have a hello world, and indeed I'm running on ARM 64 bits. So yeah, wouldn't it be nice if we just run cargo test or cargo bench directly on Android? And the answer is yes. I figured this out afterwards. It's not that complicated, but you need to know how it works. So what happens under the hood when you use cargo test or cargo bench is that, first of all, cargo will compile a test binary, which is the same for test and benchmark, by the way. And you can get it with this no-run flag. And then, secondly, the tests are invoked, or the benchmarks, and you get a terminal output. And what you can do is register with cargo a special custom runner that will take this test binary as input and do whatever you want it to do. So here, with this Android debug bridge command, we can push the binary directly to the Android device. So it's directly a plain binary. It's not even an Android app, but because Android is a Linux system, fundamentally, you can actually just spawn a shell and directly run code this way. And so that's what I do next. you run the binary with this shell, and you get the output directly in your terminal, which is much more convenient. And yeah, the way it works is you have to register this runner script. You can do whatever you want, and as I explained, what I want is to push the binary and run it. All right. So yeah, after all these steps, I now have Rust code with SIMD running on my Android device, but I still need to detect which instructions are even supported. And yeah, the reason for that is that these SIMD instructions are kind of extensions on top of the CPU architecture. And if you look at the Rust documentation for the intrinsic functions, you will see this yellow notice, which I think is the kind of unsafe guarantees that you have to uphold. That, for example, this specific function is only available on ARM, so that's fine, and only for CPUs that have this Neon and AES features. So yeah, the thing you have to keep in mind is that each CPU model will support its own list of or set of target features on top of the baseline. And if you run unsupported instructions, it will crash the application with illegal instruction, or maybe you get undefined behavior, probably even. you get. So, you know. That's why I took my old device. I didn't want to, crash it. Yeah, so basically you have to make sure that this is that your device supports this instruction, and if it doesn't, you need to fall back to a fallback implementation that doesn't use all the speedups of SIMD. And Rust offers two methods to detect these features on the current CPU. It's documented in this CPU feature detection page. The first one is called static detection, is actually to not detect anything. You just assume it at compile time with this target feature flag. And well, yeah, this will crash your program if run on an unsupported CPU. Otherwise, you can use this macro provided by the Rust language is Arch feature detected. You call this macro at runtime and then validate that you have the correct features. So how does this macro look like? You just pass it a string. The list of strings available is fixed in the compiler, and it returns a Boolean true or false depending on what is available at runtime. So yeah, I run that on my old device, and unfortunately, disappointingly, it only detected 3 features. And yeah, the function I showed before here was required to have Neon and AES as target features, and here I only have Neon, so I was a bit disappointed that I couldn't run my test. So yeah, I just thought, okay, well, what if I run it anyway? Maybe it's UB, maybe it works. Let's at least give it a try. So yeah, I did the following. I just detect that Neon is supported and then call the my nice function here. So here I'm following the template of the Rust documentation about this dynamic feature detection. And so yeah, at the bottom I implement my SIMD specific function, which is unsafe and has this special label about target feature enable equals the features I want to enable. Yeah, and so here I just call the instruction itself to validate that the output bits are the inputs are consistent with the inputs I expected for my test. And I also return a static string just to confirm that this dispatch was to the dynamic function was correct and that I indeed run the SIMD instruction. And turns out that it worked. So yeah, I was very surprised. I was wondering, okay, what is going wrong here? Is the labels put on these intrinsics, are they incorrect? Or is the feature detection not working properly? Yeah, so let's dig a bit deeper. So what happens behind the scene of this is Arch-specific macro feature detected. On Intel, it's very simple. You have a special CPU ID instruction that you can run from anywhere, and it just returns a bit flag. So you can just read these bits and confirm which features your CPU is supporting. On ARM, there is also a special instruction to do that, but unfortunately, it's only allowed to call it from kernel mode. So if you're in a user space, you cannot verify what features are supported, which is a bit disappointing, but that's how it is. So in practice, what happens is that the operating system will implement an API that you can call, and the operating system will call the special instruction for you. And yeah, on Linux, you have 3 methods for that, on Linux for ARM, that are implemented by this std detect crate, which is part of the standard library. Either you call a special function or you read some files from the special proc file system on Linux. So I tried to implement these functions directly myself, and yeah, it turns out that calling these methods was on my device detecting more features than what Rust detected. So it seems that this macro is a bit broken. And yeah, the root cause of the problem was the following. So Android is kind of a Linux-like system, but the macro didn't recognize it as such. So as I mentioned, on ARM, there is OS-specific detection code to run. So there is this dispatch code, and this is based on the target OS string. And the thing is, for Android, the target OS string is set to Android and not to Linux. So here this block for Linux wasn't called. Instead, there was just a fallback at the end, which basically as a fallback was not detecting anything because it cannot do any better. So yeah, that was the root cause of the problem, which led me to my first patch to the Rust compiler. I mean, it's just a few bytes, but I was very happy. And also, thanks for the Rust compiler maintainers, the review was really fast. I don't know, maybe an hour or something to get the first feedback. I mean, I think within a day it was done, you know. And yeah, so with that implemented, I had 4 more features detected. Yeah, I just want to mention about this patch. You know, before sending my patch, I wanted to be confident that it actually works. So I had to build a local Rust compiler to test my patch. Who here in the audience has compiled Rust-C before? Okay, like 1/3 of the people. So that's good. And yeah, I mean, in the beginning, I was a bit daunted by this process. I thought, oh, well, Rust-C is a big thing and so on. But it turns out that the building guide is actually quite good. Yeah, so I had to run this Python script with setup and build a stage 0 compiler. And then on Android, the NDK is everywhere, including in the compiler itself. So I had to inject that into the config. So again, once you know how to do it, that's good. Otherwise, you can spend some time. And then lastly, I had to build this stage 1 compiler, which, as I understood, is more or less compiling the standard library. So here for all the Android targets where, I mean, this standard library is the code where my patch was. I also needed to compile it for the host target, even though I'm never going to use this local compiler to compile for my host, but that's what was needed. And lastly, I had to add it to Rustup and just run cargo plus and the name of my toolchain build. So yeah, I think I found it also insightful, like that building Rust-C doesn't require that many resources. So I did some statistics and experiments about that. In terms of disk, for my setup of just targeting Android, I just needed 10 gigabytes of disk. So if you have even a bigger laptop than mine, you could run everything in RAM, and maybe it's even faster than that. Yeah, but if you have a slower and older laptop with only 1 CPU and 2 gigabytes of RAM, you can also do it. It's going to take half an hour, but so yeah, that was also interesting to know that compiling Rust itself is accessible for everyone. And yeah, this leads me back to SIMD and the last part of my talk, which is about performance pitfalls. So as I mentioned before, the goal of SIMD instructions is to speed up your algorithms. And so, yeah, when you're going to write an optimized algorithm, you really want to get the best performance. And on top of that, yeah, the promise that Rust intrinsics for SIMD give you is that on the one hand, you will benefit from Rust type checking. You don't have to, do all the checks yourself for the assembly. And that at the same time, you would get the best performance without needing to unroll the assembly yourself. So I did a small case study here. And yeah, to figure out if SIMD instructions are really a zero-cost abstraction. So the use case here is a bit more complex than just the example from the documentation, which was just about calling a few intrinsics. Here, in the setup, I have a function foo at the top level that will recursively or transitively call intermediate functions, here bar, and then that will itself invoke the intrinsics. So here it's a very simplified example, but let's say, let's say that foo is at the top level my hot path, so I want to inline everything in foo to get the best performance. And also, let's say the logic in foo itself is just calling bar, doesn't depend on SIMD per se, so if I want to write a fallback implementation without SIMD, I don't want to rewrite everything twice. I mean, it might be that, there are arithmetic abstractions or whatever, like in practice, you don't want to rewrite the whole code. And yeah, what happens when I compile this? So yeah, bar was marked as inline always, so that I get this inlining. And here is the output from the compiler explorer. So what is the assembly I got? You can see that the bar function got inlined into foo, but however, all the SIMD intrinsics that I called are separate functions that just basically invoke one SIMD instruction in the middle, but in between there is a lot of boilerplate to, jump to a different function, load a value from the stack, then call the instruction, write it back to the stack, and so on. So it seems like there is some overhead going on here. And yeah, when I compile the same code with the Rust flags for the target feature, so at compile time, I guarantee sort of that these features are implemented. Everything got inlined, so I directly have the SIMD instructions one after the other. And therefore, everything was 5 times faster, which is a huge difference. Like 5 times is the order of magnitude you can expect in general for SIMD. So yeah, that was quite a difference. And I think it really highlights this fact that inlining is an essential optimization of a compiler. There was a recent post by Matt Clad I encourage you to read, which was also sort of speaking about SIMD in a way. And yeah, so why were the intrinsics inlined in this case and not in the previous case? So to answer this question, let's take a look at the definition of the intrinsics in the Rust standard library. First of all, you can see that they are annotated as inline, so you expect them to be inlined. But there is also this target feature enabled with the feature name and unsafe. And yeah, the actual implementation is not some assembly, but deferring to LLVM. There is this link name LLVM and a lot of compiler-specific shenanigans. But yeah, so let's focus on the, let's say, wrapper function here. So what happens here? There is this target feature enable equals foo that annotates the function in a special way and says, okay, this function is only available for this CPU feature. And the root of the problem here is that if you have a function with this annotation and another function with different annotations, they cannot be inlined in each other. So I found this few bugs on the compiler about it. Yeah, so I don't know if it's a limitation of the language itself or of LLVM in some way, but yeah, that's something that doesn't happen. And lastly, if at compile time you explicitly enable this target feature, it's as if all the functions in your program were annotated with this feature. So now you can inline them in each other. So yeah, that explains what happened for me. So yeah, in short, if you're going to use SIMD instructions and intrinsics in particular, you have to be mindful of function calls and make sure you annotate your functions. So yeah, like I didn't really find a nice, truly zero-cost abstraction to this problem. You have to kind of choose between various solutions. One is to say, okay, this function is going to be the hot path. I implement everything inside this function. But if your hot path is complicated, it might be not ergonomic to do that. The other option is to rewrite the code twice, with and without SIMD. And here in the SIMD version, you will have to annotate all your functions, okay, with inline always, of course, but also the target feature that you enable, and therefore all the functions have to be unsafe. So we're kind of losing some ergonomics from Rust from that. Another way would be to have the code existing once, but compiling, these hot functions twice with different compilation flags and play with the linker to kind of dispatch both of them. I wrote a post about it, but yeah, it's like a lot more complicated. And the last approach is to use macros to take your input source code, and the macro will output two variants of your code with and without the features. And this is what the multi-version crate is aiming to do. I didn't dig into the details, so I don't know if it works if you call several functions transitively like this. Yeah, so that's it from my talk. Yeah, so just, as a takeaway, the intrinsics for SIMD are not perfect yet in the compiler, but they are still better ergonomics than hand-rolled assembly. And on top of that, there's this portable SIMD effort to aim to kind of standardize the common functions, the common instructions that are present on kind of all the major architectures, and give also nicer names than the intrinsics I showed before. Yeah, again, big thanks to the Rust compiler maintainers for the blazingly fast code review. And also, yeah, the compiler explorer tool was really nice to see the assembly outputs.
Let's start with offline questions, and then we'll do some online questions. What is the first one? I don't know. One of them.
Have you tried QEMU in ARM64 mode? I think it supports SIMD as well. Would be cheaper than the old Android phone, maybe?
Yeah, so with QEMU, yeah, so there's the approach of taking an emulator, of course. The question is whether the emulator will implement all of the instructions you want to test, including all the most recent ones, whether it will implement them correctly. Hopefully yes, but who knows? And then lastly, there's the benchmarking part, which is important. And I think in practice, for example, I mentioned that the hash map implementation for Rust is now using SIMD. It's not exactly true, because it's the case on Intel where the SIMD implementation is faster. But on ARM, some of the core, let's say, operations that are used in the Intel specific algorithm don't exist in ARM at all. So you have to use other ones, and it turns out that then the algorithm is not faster. So that's the kind of thing, ultimately, if you want to benchmark, you need real hardware as well. And then, I mean, here I tried on one specific device, but over time, different CPU models can implement some instructions faster than the previous generation. So, this you can only get with real hardware.
Any more questions? Otherwise, I can ask internet questions. Yeah. Let's do him, and then let's do an internet question.
Thanks for the talk. It was great. I was curious, before you submitted the Rust C patch, you were still seeing some features on your Android phone, even though you couldn't call this instruction because you weren't in kernel mode. Where did they come from? Was it just a guess from the compiler? Or?
Yeah, so really good question. I didn't prepare a slide for it, but it turns out that each, let's say, Rust target triple, which is the combination of the OS and the CPU architecture and things like that, can already define some baseline features. So for example, here on Android, the Android docs somewhere says that all the Android devices are required to have this neon feature, which I think is quite common as a baseline for ARM64 nowadays. Maybe not all ARM64 will have that. But anyway, so somewhere in the compiler, the definition of Android for ARM64 will hardcode these features. And so, yeah, the macro here is kind of doing the right thing of not doing any runtime detection if you provide, you guarantee at compile time that the features exist. So either by, it being embedded in the compiler, or if you add this static detection by compiler flags, it will also show up here in the macro, and yeah, the macro will not generate any code. You will just have a true constant replace. So hopefully, then the compiler can also dead code, eliminate the other branch as dead code and things like that.
Oh, now we'll do some internet questions. First one is pretty fast. Are there many assembler style that the inline macro supports?
So this one, let me go back to it. So I think, beforehand, this macro was, before it was stable, it was called LLVM ASM. Which was using the kind of an LLVM specific syntax. I don't know if it's AT&T or Intel, but nowadays it's kind of a Rust specific one in the sense that like the compiler will detect these things like, this print style blocks that X is a register of a certain type and so do some checks. Style. So yeah, there is just one style in this macro, yeah. I mean, presumably you can have assembly in a file and compile it separately and kind of inject it in another way, but I didn't try that at all, so yeah.
Have you looked at other languages like C++ or this Carbon language?
So for now I just focused on Android, on Rust, sorry. Yeah, I was very interested into how does it work in Rust specifically.
All right. Final side note, there is a testing farm for free software from the Free Software Foundation, so I will introduce you to that. Are there any more questions? Otherwise, we'll take a break. Yes, final question.
Yeah, but the device farm, I think like there are a bunch of fundamental crates, like I mentioned the hash map or the string searching or things like that. And I guess, yeah, these kind of crates might be interested into this kind of CI for various platforms because
it's more interactive actually.
Yeah.
You get the shell. It's not CI. You can have CI, that's a different story. So.
Yeah, but I guess that would be already a start because sometimes a maintainer writes a crate for Intel. They don't know anything about other platforms, and then the library doesn't implement SIMD on other platforms, so it's not as blazingly fast as it could be.
in your benchmark, you mainly tested just the intrinsic itself, but if you also did you also think about the difference if you included the feature check macro, how that would affect the performance at runtime?
Yeah, so like on the blog posts, I have much more details, but yeah, I also compared like on a whole program, what happens if I just do static detection, so at compile time or at runtime, and what was the cost of that. And I think, like for me, the idea was that if I was going to put a check for each intrinsics, I'm going to call the runtime check many times, but most importantly, like the inlining will not work, so it will worsen performance. And if I put the check at a higher level function, which was kind of the what drove me to this, then there will be fewer checks, and within the checked block, there will be more opportunities for inlining. So it really depends on where you put the check. I mean, otherwise, apart from this inlining problem, the check itself is kind of cheap in the sense that the macro will cache the results into a global variable and only call it once. So, if you're in a hot path, in a hot loop, calling the check macro all the time, hopefully your results will be cached in the CPU or maybe in a register. So, like loading the bit for memory will not be the highest cost. I think it's more the optimization cost of inlining or not that will matter.
Okay,
I think.
thank you.
But
Okay, then let's do another break. Let's say a short break to 2015, and then let's continue with Andreas' talk.
Okay.
Keeping the property that we wanted, right? We want to say that that property is valid for the return value. And the error message we get from Varus is different. It's not a panic. We actually never run the code here. what we got here is two messages that say that this assertion failed. But Verus doesn't run the code. What Verus does is it statically checks every possible way to that this program could run, and checks whether these assertions are true in every possible case. Now, you're going to say, well, this is not going to work because this function is bugged. And I'm going to actually take the opportunity here for a second to introduce you to another concept in Verus, which is, despite me fixing the function right now, the tool is still not believing me. It's still telling me, well, these assertions are not true. The reason for that is that Verus, for various reasons, is modular. So it requires you to provide a specification for every function that you're trying to verify. And so what I did here was just to move those assertions into this ensures clause. And we're saying for this function, we want the return value to be either of the inputs and the greater of the two ones. So now if I run Verus on this program, we get a new error message which says failed this post condition here, and it's pointing out to exactly where the problem is. And that's happening at the end of the function body. There's only one return here, so this is easy. So as you can imagine, we can go ahead and fix this, run it again, and now finally Verus is happy with our program. It's saying the function is verified. So interestingly, once we have done this, conceptually, we don't need to write any tests anymore. Verus has just proven that for every possible A and B that you could pass to this function, these ensures clauses will hold. So we know that there isn't a possible input that would break the behavior of this function. Obviously, this is fairly trivial. You can imagine a more complicated program. Also, feel free to stop me if anything is unclear, or if you're like, what's that? Or if you want me to try something, please ask. I'm happy to try things out. Things might break, but that's the fun of it. So, cool. So this is the verification. The promise of verification is this mathematical guarantee, this static guarantee that conceptually we've tested the function for every possible input, or tested the program for every possible input. Cool. So why Verus? Why am I talking to you about this tool and why we've been developing it? The context is that of all of the people on the first slide that you saw, a lot of them have been thinking about verifying system software as a way to have strong correctness guarantees. This is kind of the same goal as testing, but hopefully stronger. And as usual, like avoiding data loss and availability of bad consequences. But also, if we want to be able to use these techniques in the real world, we need to be able to use the verification process as part of regular development. We need to be able to build up the program while we verify it, and then keep this verification going. And also, once we've constructed the program, we need to be able to maintain the artifact and maintain the proofs that we will see will be necessary sometimes. So why Verus again? Again, we're looking at languages that we want to use for verifying system software, and if you're not familiar with the area, there is more and more interested in space, and this is moving in different ways from academia to industry. There's now verified projects and teams in various companies, but there's a spectrum of things you could use, and there's things that are easy to verify because they're more like math, and we are going to do math to try and improve properties of our programs. And there are things like closer to computers, so like whose code is closer to what you end up running on the actual computer, which is something that systems people often want. Like they want the control. They don't want to write sometimes a functional program because they don't have enough control. So Rust has this very interesting property of being on this side of the spectrum: zero cost abstractions, efficiency, predictability. It's imperative, no garbage collections, all the good things that you want from a systems language, but also happens to be closer to that side of the spectrum. So it's in some ways a functional programming language, and has things that functional programming languages have had for a long time, such as algebraic data types, pattern matching, and restricted side effects. So we think of Rust as a very good language for this. And To reinforce this, and I'm not going to belabor the point, you're probably familiar, Rust enforces single ownership by default using what's called the Rust linear type system or fine type system, depending on your interpretation. And the demonstration here is just a tree data structure. We have a left and a right node at each node. And what we're going to try and do here is to assign the right child of left to also be the left child of right, which is clearly illegal, and Rust would reject this, right? So we have this guarantee that everything is owned uniquely. So again, this is why we like Rust for this goal. Rust linear type system tracks ownership and prevents what's called aliased mutable references, which means that what we get from Rust regularly is data races and user tree, all the nice properties you're familiar with. But in addition, we have noticed that aliasing is a challenge when doing functional verification, so the kind of technique to do development as I've shown before. And when you do functional verification of imperative code, it's often required that you need to think about what the data on the heap looks like and what pointers could potentially change which parts of the heap. And that's really difficult if you don't have the restrictions that Rust imposes. So the idea here is to rely on Rust linear type system instead. And here, we were not the first one to think about this, and there are some folks on this list in this room. Folks at EDH have realized this a few years back and started on a tool called Prusty that leverages these properties of the Rust type system to facilitate verification. We're going to take the similar idea, but taking a bit of a different direction. So again, this should be obvious. Rust prevents alias mutable references. And here I'm going to start with an example that goes into why it's useful for verification. So we have this structure, struct account as a balance. We have a function transfer that takes two accounts, source and destination, and an amount to transfer between them. So these are unique mutable references, as you know. And the ensures here, which says the balances change as they're supposed to, are only true if the origin and the destination are not aliased. So just to clarify, if we tried to call this function like this would be legal in a language like Java, for example, then the result would not be accounts that satisfy that property, because we are taking away and putting back money into the same account, but not in the right way to end up with the same result. And the problem here is that those two mutable references are aliased. So obviously Rust catches this problem, and because it does, then we can rely on this to say, well, then that ensures that property that we wanted to prove is actually true. Cool. Making sense so far? Cool, great. All right, so that's why Rust. Now, why Verus? So again, the goal is to make verification, formal verification, practical for writing system software. And we started with some of the folks on the first slide using a tool called Daphne, which is a kind of C#-alike with integrated verification tools. And then, because we encountered all of these issues thinking about how to reason about aliasing when writing proofs in Daphne, we've integrated a linear type system into Daphne. So it kind of made Daphne look a little bit more like Rust. It was a fairly straightforward linear type system, but it indicated that that would have improved verification experience significantly. And so we started to think, well, we're trying to make Daphne look like Rust. Why not try to make Rust look like Daphne, which is a tool that we really liked in terms of the feature it provides for verification. I unfortunately can't really talk about more Daphne here, but you can look it up. It's a really interesting language. So that's how Verus came to be. Verus is our SMT-based intrinsic verification tool of safe Rust code. There's a few caveats. I'm going to get to all of them. Also, there's words that maybe you've not seen before. What does intrinsic verification mean? That's actually something that I was already talking about earlier, which is if we go back to our example and we try to verify it, you may know what to expect. You may know what may happen here. We haven't provided a specification for the transfer function, and so Verus can't really tell what's going to happen when we call transfer here. And also Verus is worried about the fact that we might overflow here and there. So Verus is also checking that no panics will happen. And the way we fix this, to start, is by adding what's called a precondition. So we're going to say the original balance before we call the function, this is what old overage says, should be greater than the amount. We shouldn't be able to withdraw more money than there is available in the account. And also, if we are depositing into the destination account, we shouldn't overflow U64 max. Now, if we run Verus again here, we notice that the two first errors, the two possible arithmetic underflow and overflows, are gone, because now Verus looks just at the body of this function and says, well, if we know these two things, then these two cannot possibly overflow. Yeah?
So in your second check, you have a strict inequality with max. Is that a restriction, or could you write?
That's a good point.
Less than or equal?
Yeah, no, I think it was a typo. Well spotted. Yes. Excellent question, by the way. Who verifies the verifier is a very good question. Doesn't fit in this talk.
Your transfer function has the exact keyword. What does that mean?
Great question. So we're going to get to that in a few minutes, but I can mention now that exec means that this function is something that we intend to execute. So it's program code that we intend to actually compile and execute. There's going to be other code that we don't intend to compile and execute, but I'll get to that in a second. And while I'm talking about this, you may have noticed that the syntax looks different. For example, this is not legal Rust. So what's happened here is we worked, and mainly Chris Oblitzel and Microsoft worked on this Verus macro, which you pass essentially the entire program into, or entire file into, and does a syntax transformation so that we get to use syntax that is more comfortable for using the tool for verification, but also still allows us to use the regular unmodified Rust compiler behind the scenes. So this is the unmodified Rust compiler, but with a custom driver. We get to have nice syntax, or the syntax we want, and the syntax we have learned to like from previous experiences using this macro. So you'll see Verus bang everywhere. Cool. So now we were saying that these two assertions down here are still failing, even though they should pass. And what we can do to fix that is make sure that we modularly describe what the transfer function does, because Verus is only going to rely on the specification to determine what happens when we call the function. And then we're just going to verify the two functions separately. So if we make that change, that then ensures and say, like, this is the behavior we expect, now Verus can verify the program. And I want to stress once again that we're not running the program. In fact, there's a joke in verification that people essentially never run their programs, except like 2 days before the deadline, if you're in academia. But we still get, so in theory, if Verus is correct, there is no way that this program will go wrong. And so in some ways, you wouldn't need to write any tests. There are caveats to this, obviously. Great. So that's intrinsic verification. So a whole logic specification is a description of what happens before and after you call a function, for example. I said SMT-based as well, which is one of the possible techniques you can do verification of software. There is more manual techniques where you kind of write the proof steps by hand, but as you can see here, this program, albeit simple, verifies automatically. And the way we do this is by leveraging an SMT solver. So you may be familiar with SAT, which is Boolean satisfiability, which means you have an expression, and you're asking yourself, there exists an assignment of x and y such that that expression is true. And you could do this by hand, or you could grab Z3, which is a very powerful and often used SMT solver. And Z3 will tell you this expression is true if, for example, x is false and y is true. you can try. But what we're going to do actually is go and look at that program and actually run Z3 on it. So you get an idea of what it looks like. So what I did here is just write that expression from before, from the slide, in syntax that Z3 understands. And it's kind of this Lisp-like syntax. And then what I'm saying is check sat, which means does an assignment exist? And we're getting the response sat, yes, there is. And get model means tell me what that assignment, what one of those assignments could be. And here it's saying that y is true and x is false, which is what we expected from before. Cool. So there's an extension to SAT, which is what Z3 implements, which is SMT, satisfiability modulo theories, meaning that we're going to generalize SAT to formulas that include other theories. So real numbers, integers, data structures, and quantifiers, which turn out to be very useful when doing program verification. So for example, here we're going to say, we could say that for all A and B, A times B equals B times A, and we should be able to prove that. So in SMT-based verification, what we do is we start from the program. So here I'm going to try to explain to you in 2 minutes how Verus works at a very, very high level. So we're going to start with the program, and we initially wrote this test by hand, right? But what I've been saying is, we don't really want to pick two x and y's. We want to say what happens for any possible A and B, which we define by the ensures clause. And now what we're going to do is encode things like this. So what we want to prove is that for all A's and B's, the max of A and B is A or B. So it's one of the two initial values. This is just kind of a logic encoding of this expression, and that it's greater than both, right? So what we're going to do is just turn that for all into a not exist not, which is a valid transformation. And Z3 is excellent at figuring out this exist part. So we essentially use Z3 kind of the other way around. We're asking it, can you prove that such an assignment does not exist? And if it can prove it, then it must be that for all A and B, that expression is true. And so if Z3 says sat or unknown, so there exists an assignment of variables that falsifies what we were trying to prove, then we failed. And if it says unsat, it means that Z3 can prove that there is no assignment to A and B that could falsify our postcondition. So we know that for every possible A and B, that's true. And if we're in SMT with all of the theories that we've been talking about, we are in the realm of undecidability. So Z3 will encounter programs that it will just spin on forever. And that's a fundamental result in computer science. And we can't do anything about it. In general, in practice, we can actually prove a lot of useful programs, but there is this issue that sometimes Z3 just goes off and spins and never returns. And we need to figure out how to kind of deal with that. All right, so when using a tool like SMT, we get these automatic proofs that we were seeing before for free, at least at this level of complexity. That comes with the fact that we need to make sure to use this Z3 tool properly to extract as much performance out of this. If you're seeing that it takes us a very short time to get a response, but that's a very explicit design goal for Verus of getting a verification result back quickly in an amount of time that resembles how it would look like to just cargo check something, right? It takes longer for more complex functions, sometimes significantly longer, but that's very much our focus. And we achieve this by prioritizing efficient encoding to SMT queries, so the way we encode the program in Verus. And here, I think it's interesting to actually look at almost what the verification query that we pass to Z3 looks like for this program. So I did a tiny bit of editing here to just simplify things a bit. There is a bunch of prelude that I'm not going to talk about here. Just ignore this. It's fine. It's the same for. It's almost the same for every function. But I didn't want to be dishonest and delete a bunch of stuff. So this is not exactly the spin. I think I deleted 7 or 8 lines that are not critical for doing verification here. But this is the encoding basically in Z3 of our max function. So we are saying see the not from before? We were proving that exists not something, and so that's exactly where it shows up. Our assumption is how the function looks like. So we're doing, if A greater than B, B A, and then what we're trying to prove is the postcondition from before. And we can just run Z3 on this, and if I write it correctly, we're getting unknown here, which means Verus cannot prove that the program is wrong. It also cannot prove that the program is correct. It's saying, and this is incompleteness, so meaning that Verus is not able to determine all the time which one of the two is the case, and this is, or rather Z3 in this case. However, we generally just treat unknown as a verification failure. We're just telling the user, we would be putting up to the user that message saying that assertion fails or that postcondition fails, and then the user has to come back and give us a bit more information to prove their program. Okay, so now this is unknown because it's a simple program that we expect Z3 to probably verify correctly automatically, but the program is wrong because it's the same bug as before. So I'm just gonna fix stuff so this kind of is equivalent of fixing the function definition, and now we're getting unsat. And as a reminder, unsat means proof. So we've just proven that for every possible assignment to A and B, that program will always return something that satisfies our specification. Cool. So I've shown you smaller examples so far. I want to get once into what it looks like to verify something a bit more complex. And the example here is the iterative implementation of Fibonacci. So what we're doing here is just wrote the code, the executable code that we want. Exec is back here again because that's the code we actually want to execute. However, we need to be able to say what correct means in this context. And what we're going to try to do is say, well, we need to make sure for this function, we'll need to make sure that the return value in fact fits into a U64. Otherwise, we're not going to be able to return it. So we need to call it with an end for which Fibo will fit. And the ensure says the result is the Fibo of that number. But what does that mean? Well, in Verus, we have this other part of the language, which is essentially a functional language, functional mathematical language, which now is marked spec, that lets us describe the intended behavior of the program in a more abstract mathematical way. So this is the definition of Fibo that you would expect mathematically, and then Fibo fits U64 is just that. So let me run Verus on eFibo1. And what we're saying is, and Verus is saying, okay, not quite. This postcondition we cannot prove, and this might overflow. So here is where we have specified the function fully, we think, but SMT, the Z3 is behaving in such a way to avoid spinning off uncontrollably, and so it holds back in trying out potential proofs, and so we need to guide it a little bit. And the way we do that is by writing proof functions. So here, I'm not going to go into how we got here, but we're going to say we're going to need to know as a theorem that Fibonacci is monotonic, and in Verus a theorem is just a function with the keyword proof in front. And this is saying for I less than j, then Fibo of I is less or equal to Fibo of j. And we need to also prove that this function terminates, but that doesn't really matter here. I'm not going to get into how the proof exactly works. The fact that we are calling itself, if you remember proof by induction, that's exactly what we're doing explicitly. We are using knowledge about in inductive cases to prove this current case. And but again, I'm not going to go into exactly the details of the proof. And if we try and run Verus on this, so because we don't get an error, Verus actually can prove the Fibo is monotonic lemma. We just aren't using it yet. The way we get to use it is first we need to add an invariant. So whenever there's a loop, Verus will not actually infer some of the, or in fact, all of the invariants that need to remain true for the loop to prove the postcondition. So we have to explicitly say this is the loop invariant. And then the other thing we need to do is to add this proof call that says here we need to prove, we need to use the knowledge that Fibo is monotonic for I and n, in this specific case, to support that this will not overflow. And there's a few hidden steps that Z3 does for us. So now, hopefully, if we run it on 4, we get a proof.
I have a question.
Yep.
So, I lost it. So the question was, how do you handle the bidirectional type system? But we don't have to explicitly type all the things, so we have let something. How do you handle?
Oh, you mean like type inference?
Yeah, type inference. Yeah.
Okay. We just do whatever Rust does. So all of this code gets passed on to after transformation. It actually doesn't look that different after transformation. Just looks like Rust, and we just rely on the Rust type checker, which is one of the big benefits of building a tool on top of Rust, is that we have access to all of that type system and all of those features from the type system. Okay. There are details in which we need to be very careful about the assumptions that are baked into the type system by Rust, and how we expose those assumptions, and how we treat, how you write your code so that those assumptions are upheld, and so.
So you use the high-level intermediate language, I assume.
Oh, great. So like how technically, so yeah, the different tools do different things. What we do is we take HIR and use that to generate the queries. Like there's a few layers of transformation, but basically we start from there. And then we at some point run the borrow checker. I'm gonna get to exactly the fact that we don't always run the borrow checker with
all right, thank you.
yeah, thanks. Great question. So great. So this is, this Fibonacci function is now verified for any n that fits into U64 to actually compute Fibo. Cool. So this is all of the code in that proof, and I'm gonna highlight some of it and getting back to your question before. So this is exact code mostly. This is the code we actually want to run. This is proof code, so it's code that we used to explain to Veros and to Z3 why our program is correct. And this is spec code, so this is how this high-level mathematical language, kind of function language, in fact, this allows mutation, for example, that lets us specify what our program should do and lets us talk about some properties of the program. What's important here is that spec and proof mode code are ghost. Ghost meaning that all of this code will not appear in the final binary. It's only there for us to express what the program should do and to prove it correct. Great. So the interesting thing in Veros is that we treat, this is not quite exactly accurate, but it's I think a decent approximation, which is that we have 3 modes of code that we've seen, and we only type check spec code. We don't borrow check it. Which means that you actually can violate some of Rust's restrictions on aliasing in spec mode code, but that's sound because spec mode code is just a functional language. Proof mode code is treated as regular Rust, but we erase it before we get to compilation, and so that lets us express some proofs, and I'm going to show you a quick example in a second. And then exact mode code is just regular Rust program. We want to run that program. We're just going to compile it. Borrow check it first, then compile it. Okay, so as mentioned, the Rust type system, something Veros relies on for its correctness. We do rely on the fact that Veros guarantees that for runtime values, there will not be alias mutable pointers, mutable references. But Veros also allows us going beyond what Rust supports, and hopefully without any UB and any unsafe in the kind of regular Rust sense. It's always terrifying to say a sentence like this with Ralph in the room, who just gave the talk from before, because there are a lot of details in getting things like this right, and this is a work in progress. So there may be still areas in which we have missed some soundness guarantees. We'll try to be very careful about soundness and only add features to Veros that will be sound, but the safety properties around code of this kind are complex, as discussed by Ralph earlier. And so Rust allows unsafe to break out of linearity. You get to do aliasing in there if you do it right. And Verus allows access to some other set of primitives that we wrote that are like pointers, the raw pointers, for example, that let us interact with these normally unsafe features in a safe way because the verifier is checking some of the assumptions. And here's an example. This is a bit involved, so I'm just going to try and go over the concepts. But what's happening here is we have a transfer permission function is just saying, this is some ghost state that we use to describe the program that we're going to transfer away. Store copy of pointer just stores a copy of the pointer we pass it to. So think of PPTR as just a star mute U64, but our version that's conditionally safe. And things like PPTR put is like assigning to 5, but there is this additional argument here, which I'll get to in a second, and then take is essentially like PPTR assigned to null. So what we are saying here is we are going to allocate a new pointer. It's going to point to nothing. Then we're going to give a copy of that pointer to somebody else. The pointer is just copyable. That's fine. We know that it doesn't contain anything. Then we're going to store a value of 5, and that should be worrying to you. We just gave a copy of somebody to somebody else. That somebody else may spawn a thread and go and write into it. That's not great. That could be a data race, and that could be undefined behavior. However, we get to do this safely here because we have this tracked permission, which is a ghost, is some abstract representation of the fact that we can access the pointer, and that's treated like a regular Rust type, so linearly, so you don't get to alias it. And because we are still holding on to the permission, then we know that we are the only ones who would possibly be doing this operation at this point. And then once we do that, then we know that the contained value is 5. Then we try to transfer the permission elsewhere because with some more complex proof around it, which I'm not going to be able to show, we're going to say somebody else now gets to write here. But this is totally a ghost operation, so it's not going to appear in the program code at all. And then we try to delete the contents of or set the pointer to null. Now, this program I'm showing is actually broken because after we've transferred the permission, we should not be able to set the pointer to null because that could, again, be a data race, right? And so here, the cool thing is that we get to rely on Rust borrow checker to check our proof. So this is some high-level, more complex proof and access to permissions, which is kind of a separation logic inspired for those of you familiar. But we have this nice interface that is given us by the fact that we are relying on the Rust type checker. Okay, so, and this is why we have this proof mode, which is this program, this style of code that is borrow checked but isn't then compiled. And all of those are all the fragments that are in fact proof mode here. And as a reminder, those are ghosts, they go away. So we are not spending any runtime resources on transferring this permission. The alternative here would be at runtime, we transfer an owned box elsewhere, but that wouldn't require a channel and then that transfer explicitly. Here, if we can set up a protocol around this to control how this permission is transferred correctly, abstractly, then we get to do it without any runtime cost. Okay, so generally speaking, we're designing Verus as a pragmatic toolbox for verification. We've seen that we want to encode it to SMT queries efficiently so we get good verification performance. We have support for things other than Z3 and separate Z3 modes to reason about specific things that come up a lot in system software, like nonlinear arithmetic and bit vector. And also, we've been working on shared memory concurrency support. So if you want to reason about a concurrent programs, we have techniques to do that. And this is based primarily on work done at CMU by Travis Sanz and other folks. And what I wanted to showcase here is how does it look like if you want to use a different prover. Here we're going to try to prove some property that if we divide x by y, then the result is smaller. We get to use the nonlinear arith prover to do that, which is geared towards exactly that goal, is hopefully more efficient. And then we can do bit vector arithmetic and do verification using that. And these sidestep the issue that the Z3 is sometimes not great at doing all of this reasoning if it's mixed together. So it allows us to be very specific. Okay, so again, around Verus as a programmatic toolbox verification, as researchers, we want to scale up verification to real-world systems so that people can benefit from these techniques. The cost is still high, but we believe we're bringing the cost down as a community. And so it's starting to make sense in the industry to verify some systems, some kind of high value systems. And hopefully that will continue, the cost will continue to go down so that more people can use tools like this. But as researchers, we want to prove that Verus works or is usable at some level. And so we have been working on, and folks in different institutions have been working on different projects around using Verus to verify different things. So there's a project verifying the correctness of Kubernetes controllers. There's a project led by Matthias, who's in the room, on verifying the page table code for an operating system kernel, and more in general, how to verify an operating system with techniques like this. And there's more that we're working on, and it's to come from a bunch of institutions. So very quickly, I mentioned that we're using just unmodified Rust mostly, but we have this situation in which we have this ghost code that we want to appear in the source, but we want to make disappear before it makes to the compiler. Rust really doesn't understand this, because why would it? Why would you want to write code that doesn't appear in the binary? And so we have been working with a bunch of folks in the community, folks at ETH from Prusty and Xavier, working on Crusoe, which is another verification tool, to add support for ghost code to the Rust compiler. And we'll be making some progress here. Great, so talked about Verus. Verus is our toolbox for system verification. All of these people on the slides have worked on Verus, and these people are not in any specific order. So Verus is an open source project which spans a bunch of different institutions. I want to highlight, because we are at ETH, that the first few tens of thousands of lines maybe were written by Chris Oblitzel, Microsoft, and me while I was at ETH. So I want to acknowledge ETH for that. But a lot of these people have had input even early on the design of the tool. So if you're interested, try the guide. Try Verus. We have this, thanks to folks at CMU, we have this cool play Rust-Lang alike over there. There's a paper if you're academically minded, and if you have questions, you're trying the tool, things don't work, get in touch, either on GitHub, just open an issue, or shoot me an email. And yeah, I think with that, I'm done. Yeah.
Thanks for the talk. I was really curious about this P pointer thing. So you know about Ghost Cell?
Yes.
So is this more general? I'm trying to understand. Is this because you can transfer the permissions in the proof? Is this the idea?
Right. So Ghost Cell is the branded lifetime, right? Nice. So Ghost Cell, let me say this correctly, hopefully. So Ghost Cell has this technique where the permission is encoded as a branded lifetime, essentially, and then you move around the permission. And that's mainly encoded just in the Rust type system. That means that you don't get to use the tool's reasoning to determine how you can move around the permission. So using this, be vague, I'm happy to be more precise later, but with Verus, we get to, so things like PPTR put has preconditions that are checked by the SMT solver. So we get a lot more flexibility on how we transfer the permissions. We can combine permissions into like a linear hash set, for example, like linear ghost hash set, and then you get them out when you need them, things like this. So we get to rely on the SMT solver in addition to having the syntactic element that kind of proves your ownership. Yeah.
Thanks.
Yep. Good question. Yep. And Ralph, correct me if I'm wrong.
I don't have a question, but it's a comment. Oh, okay. To add to that, the one way to think about it is the hard part with separating the permissions from the data is to still know which permission is for which data, which Ghost Cell does with this branded lifetime trick, which is super tricky and unergonomic and everything, but the amazing thing, it works in the Rust compiler without anything extra. Varus doesn't have the need for any such crazy hacks because they can just use all the extra machinery they have for reasoning about values and like all the SMT support to do that reasoning, and then you don't need the brands and stuff. So it becomes a lot simpler.
Yep. Thank you.
My question is about practicality. So let's say in the practicality spectrum of which kind of programs can you verify with that? For example, can you verify like sorting algorithms?
Yeah.
Which I think, there are lots of even newer algorithms that are more optimized or whatever, but are they correct?
Yeah. Sorry, is there more to the question? Great. Great question. So yeah, you can verify things like algorithms. In fact, the state of the art is pretty good at verifying individual algorithms, especially if they don't have side effects. So if they're kind of this is not a sorting algorithm. I think we have a sorting algorithm example somewhere, but I just had this is just reversing an array, which is much simpler. But you can imagine that this gets more complicated when you try and think about sorting algorithms. Sorting algorithms, because they don't, have usually concurrency and have less communication with the rest of the complexity of the system, are something that a lot of tools do fairly well at this point and very quickly, and we can do as well. The state of the art is multiple thousands of lines of programs. The largest projects I know of are, one of ours in Daphne was very better KV, which is a verified key value store, which I think is about 5,000 lines of source. There's projects in using the cog prover. I think Daisy NFS is one of them, is a file system, which is a verified file system. Completely different technique, but I think of a maybe comparable scale. And I know that there is a Wave, which is a verified, it's not fully, it's not full functional correctness. So Wave is a runtime for WebAssembly, and they don't verify, my understanding is they don't verify that it runs WebAssembly correctly, but they do verify that the runtime will not do anything that it's not supposed to. So WebAssembly is supposed to be, sandboxed, and so they verify the sandboxing property. And so the scale we are at now is multiple thousands of lines of code, multiple, PhD years of effort. That's hopefully where we are trying to improve on. So, in fact, the verified page table project thing was successful in that sense because we got very good verification time, so the iteration time was good. You can ask Matthias how frustrating it was afterwards. And it's a sizable program with very complex interaction with the system. So, page table is writing to the page table memory or whatever. Good question. And if you gotta catch a train, feel free to run.
Yeah, it's 9:05. How does this interact with memory allocation or memory allocation failure?
That's a great question. We currently assume that allocation is not going to fail. And we could have a separate API that does not make that assumption. The advantage of allocation failure is that in Rust regularly, I think it just crashes, which is not ideal for a verified program, but not the worst outcome because you're not going to do anything horribly wrong. One interesting thing about at least these kind of techniques is you're still proving partial correctness anyway, which means you're not going to actually prove that the program will terminate. So a program can just also spin forever and be considered correct. There are techniques to also address that. So there are limits, but for sure, allocation is something that currently we assume to always succeed. And if we want complete soundness from that aspect, we should probably also check every allocation and assume that I can handle, and the user would have to handle the case of the panic. In practice, many systems just make that assumption anyways, and it's a pragmatic choice. But for some environments, you would need something else. Does that answer the question? Yeah, thank you.
All right. You said that you support some kind of concurrency primitives in the language, so you're able to reason about concurrent programming.
Yep.
So you can do stuff like prove non-existence of deadlocking.
So, great question. Non-existence of deadlocking is what people call liveness usually, and liveness is hard. Turns out there are techniques that are being developed that are making that general kind of understanding of liveness maybe not as true anymore. We focus on correctness, so the concurrent program results in the correct produces the correct result, and there are no data races, there are no concurrency hazards. So we're focusing on that aspect, and a verified program in Verus using the concurrency verification techniques could very well still be deadlock otherwise. Great question.
All right, any more questions?
So far, examples that I saw, they seem like to verify within a body of the function if things are. What about across the calls, like in the continuation style, or you sometimes execute a bit, then the data goes somewhere else, come back, and you continue, and you would like to verify that the whole flow is correct.
Right.
And yeah.
Yeah, great question. So if it's just a regular function call, like we were doing for I think here, the transfer function, what happens is that we do this module verification approach where you talk about what the transfer function does, and then that lets you thread that knowledge through the transfer function call. I think you're also asking things about like a continuation passing style or like async essentially. And we haven't looked into async yet. We think a lot of the techniques may transfer fairly well, at least the non-concurrency reasoning ones. I'm not going to make any statements about concurrency. But generally speaking, this style of tools requires you to build up your verification using this modular style. So every function will carry a specification that says what it does abstractly, and you can abstract quite a bit, fortunately. And then if you have big programs and complex programs, the technique that Verus optimizes for is a state machine refinement, which is using the kind of iron flate style, if you know what that is. And which means that you essentially have this very high level description of what the program does. So for example, a key value store is just a map from keys to values. And then the transition you can have is just insert a new key, read a key, for example. And then you progressively refine and write proofs that those relationships are preserved down to a level where you have all of the operations. So the operations might be perform this read on disk, get the result of this read from disk, and all of these map to some high level operation. And that's the style that the Iron Fleet style uses. There are different techniques, but transition systems and TLA style systems are fairly common. Just for throwing some keywords for you.
Turns out these keywords are also in the online questions.
Mm-hmm.
So, to the online questions. One is, are you aware of quantitative type theory, and what do you think of this application? Or is it not relevant in your case?
I don't remember what quantitative type theory is.
Me neither. Just
does somebody
stuff.
know? Yeah.
The type system used by Idris, where each value is annotated by how often it can be used, either 0, 1, or unannotated means undefined.
Great. So I think that's an extension of a linear type system. Like it's a linear type system with more flexibility.
It supports both irrelevant and linear types.
Yeah, great. So let's see. I don't know. I think there's an interesting answer here, but it may be long. Whoever asked this, please get in touch. So let's see if I can make it quick. So linear types, we think is a very convenient interface for the kind of style of writing, but there's been a lot of success using separation logic, which is a style of type system in which the values can be used multiple times in certain ways. So you get to take a value, split it up, and then give fractions to everybody. So there's definitely overlap there. Our techniques are very much inspired by those. The relationship with Iris, I really don't remember much of Iris. I looked at it at some point, so I'm not sure. But yeah, if you're interested in more, just get in touch. Hopefully that's satisfying enough.
Mm-hmm. And a final question, can you handle string-like things?
Yes. Not a lot so far, but we do have a basic support for strings where you get to use string literals, and you get to concatenate strings and do some string operations, and then kind of prove that those result in certain things. We're, I think, lacking a little bit in the parsing, and currently lacking in at least for string, in like parsing a string and determining that the value, the integer you get, corresponds to the string value. Yeah.
Cool. I think that will conclude the questions. A big round of applause, please.
Thanks a lot for the questions. Can I?
So a final little thingy I want to announce is, screen is gone. Anyhow, the next meetup will be on the 2nd or 3rd of July, beginning of July. And we have a new website, which unfortunately you cannot see because of our nice setup. But I would love to see you all there. And I think next time we'll be going back to 2 talks because 3 is a bit long. It will be sponsored by Tippi, which are sitting over there. And there will be some food on the rooftop, weather permitted. All right? Thank you very much. Stick around and goodbye.